Hello everybody, this is Dr. Christopher White, and now let's get back to looking at what's going on in the Earth's interior. Okay, so how do we know the composition of the Earth's internal layers? Because we know they're there, but the question is, well, how do we know what they're made of? So we can get direct samples of the crust. That one's relatively easy. So we can get the oceanic crust, we can get the continental crust. You can just walk outside of a hammer or just, drill through the seafloor in a ship. However, how do we get pieces of mantle rocks? Well, we can get pieces of mantle rock in a couple of ways. Well, the first way is as xenoliths. So a xenolith is a foreign piece of rock within intrusive or extrusive igneous rocks. So essentially it's a piece of rock that shouldn't be there. So sometimes as a magma moves from the mantle up into the crust, it will sweep up pieces of mantle rock with the magma as it goes. And sometimes these pieces of mantle rock will make it all the way to the surface. They'll be erupted out through a volcano and we'll be able to come along later and find them. The other method through which we can obtain pieces of mantle rock is through the process of obduction. So I'm sure you're all familiar with the process of subduction. That's when a piece of oceanic crust goes underneath a piece of continental crust or another piece of oceanic crust. However, every once in a while, sometimes that process does not function correctly. And instead of the piece of oceanic crust going under the piece of continental crust or the other piece of oceanic crust, it will instead go over the top of them. So this is the process of abduction. And so what this means is you can have a process by which you are pushing oceanic crust over another piece of crust, let's say in this case continental. Now this means not only will you have the oceanic crust pushed up onto the continental crust, but you will also have the piece of mantle rock attached to the bottom of it. So what we have is this, these upper mantle rocks attached to the base of the ophiolite, which we can then go and look at. So these are mantle rock xenoliths in a piece of volcanic rock from New Zealand. And what can you see? Well, you can see first of all these xenoliths are small, so there's a Canadian penny for scale. You will also see though that they are very, very pristine. The minerals in here are looking great condition. But the question is, are these pieces of rock that we can see here, are they actually representative of the upper mantle? I mean, each one of them is only a few centimeters across. So can you definitively say as a scientist that what you have in front of you there is representative of what's actually happening in the upper mantle? The answer is not really. So, okay, then we go to the ophiolites. Now, just to give you some idea of the kind of scale that an ophiolite can be. So we're in the Arabian Peninsula here, and if you look, we're down in the eastern side, so we're over in Oman. And this red area here is the Oman ophiolite. So this is a piece of oceanic crust that's been pushed onto the continental crust. And so what you can see here is you can see this thing is absolutely massive. So there's a 50-kilometer scale bar, just to give you some idea. This thing is about 400 kilometers in length. So there's absolutely vast quantities of mantle rocks that have been pushed up, and that's absolutely great. The problem is that mantle rocks don't do particularly well when they're exposed to the atmosphere. Mantle rocks don't mix well with water. And so what will happen is your mantle rocks will very, very quickly be weathered, and they will very, very quickly begin to break down. So, one of the classic processes that in theory can take place is when you're, mixing your olivine-rich rocks like these here with water, you can sometimes get the process of serpentinization taking place. So the olivine-rich rocks will begin to break down. And so this can unfortunately mean that mantle rocks in an ophiolite setting are not nice and pristine like the ones we see here, but they are in a pretty bad state. So what this means is ophiolites are good when it comes to kind of seeing bigger scale structures, kind of understanding what's happening on a, in a bigger picture setting. However, you can't get the kind of, high level chemical information that you can from a xenolith. Either way, though, they do give us, a reasonable idea. When you combine the two together, they give us a pretty strong idea of what's happening in the upper mantle. Okay, so we have the crust, we have the upper mantle, and so the question is there anything else, that we can find out? Well, yes, there is. So, what's happening in the core? Or more accurately, what's the core made from? So, we know the diameter and mass of the Earth, thanks to Isaac Newton, and so we can calculate the average density. So every cubic centimeter per per bit of the Earth should, if it's completely homogeneous, weigh 5.5 grams. However, when we weigh crustal rocks, that's continental or oceanic, we see that their density is only 2.5 to 2.8 grams per centimeter cubed. So, okay, we're missing some mass there, aren't we? And then you think, it's okay. Mantle rocks, they're made of magnesium iron silicates. Magnesium, iron, they're heavy. Well, obviously, the mantle's very, very thick, so that's okay. That means all these, all this extra mass is going to be contained within the mantle. Well, when we weigh mantle rocks, we find that mantle rocks have a density of 3.2 to 3.4 grams per centimeter cubed. So there's even more mass missing. And so, this mass that should be essentially there is not in the crust, it's not in the mantle, so that means the only place it can be is in the core. And so that means obviously there has to be something very, very dense, very, very heavy at the center of the Earth. So this table of data here shows you some of, the chemical compositions for a few different things. So this is for a Cl chondrite. This is essentially the stuff that the Earth formed from. This is something which is referred to as the bulk Earth. So this is a modelled composition of what the Earth would have looked like, right at the beginning. This says this is the bulk composition of the Earth. So the Earth is made from, 31.9% iron, 16.1% silicon, etc., etc., etc. Now, this is a modelled composition, but, we use this quite a lot in geology. Here we have a averaged composition for crust, a averaged composition for the mantle. And so, right, let's have a look at what's going on. Well, the first thing we notice is as we come down and compare it, okay, the crust and the mantle, well, they're quite rich in silicon compared to the bulk Earth. Once again, they're pretty rich in calcium. Let's see, they are, the crust is pretty lacking in magnesium, but the mantle's very rich in magnesium, so that's okay. Let's see, nickel. No, nickel's missing. Sodium, plenty of sodium in the crust there. What about aluminum? Plenty of aluminum in the crust, and actually quite a bit in the mantle as well. So, okay, what about iron? Oh, there we go. So, the bulk Earth has about 30% iron in it. The crust, on average, has about 5% iron. The mantle has about 6% iron. That means there is a massive quantity of iron which is unaccounted for. Same goes for the nickel. There is a very large amount of nickel which is unaccounted for. And so that nickel and iron has to be somewhere, and so obviously you then, very quickly have to come to the conclusion that the iron and nickel is in the Earth's core, and that explains why the Earth's core is so dense. So the final thing is okay, well, we've managed to work out that the Earth's core is made of iron and nickel. So the final question is there actually any way of us getting a direct sample of it? And for the Earth, the answer is no. We can't get a direct sample of it. However, there is another way that we can get a direct sample, and we can get them using iron meteorites. So here's an iron meteorite there, and this is an iron meteorite that's been sliced through and polished. So what's going on? Well, an iron meteorite is the core of a planet that got destroyed. So remember we were discussing how, during this final phase of planetary accretion, it would have been very chaotic. these large planetesimals will be flying around, smashing into each other, destroying each other. Well, that would mean that as these large planetesimals smashed into each other, sometimes the cores of these large planetesimals would be essentially blasted into space, and they would solidify and they would form these iron meteorites. And so this is what we have in front of us here. It's the core of a destroyed, essentially, planet that never quite made it. And so what we can do is we can sample this iron meteorite, and well, what do we find? When we sample the iron meteorite, we find that it contains about 85% iron, about 5% nickel, and about 6% silicon, exactly what the modelling would suggest the Earth's core is made from. So everything lines up very, very nicely. I should point out, by the way, that iron meteorites will very commonly have this very, very intricate texture. It's called Widmanstätten texture, and it's very, very commonly seen in meteorites. So okay, so we've managed to get pieces of the core, and we've managed to work out what the core should be made from. We found pieces of the core from other destroyed planets, and they match our models, and so we can feel relatively confident in our hypothesis of what the Earth's core is made from. So we know. So now we know which layers are solid, which layers are liquid, and we also know what their chemical compositions are. So brilliant, we've done pretty well so far. So our next question is, how did the core form? Well, okay, let's think about this one. So right, don't forget, our planet at this point is completely molten. Okay, from the center of the Earth to the Earth's surface, it's 100% magma. So the magma ocean that formed the Earth contained too much iron to dissolve into the silicate magma. So there was just so much iron in this liquid, in the silicate liquid, that it couldn't, there was just so much iron that it couldn't dissolve anymore. And so, well, what's going to happen to all this extra iron? Well, the extra iron has to essentially form what's referred to as a liquid, has to form its own liquid. And it just so happens that when you form an iron liquid in a silicate liquid, the two liquids are immiscible. They will not mix with each other. Think oil and water. So what you end up with in this magma ocean is you end up with a silicate magma, which is what most of the magma ocean is. And within that silicate magma, you have these blobs of iron liquid floating around. Now, over time, these blobs of iron liquid will essentially coalesce with each other until they reach a sufficient size and weight, at which point they will begin to fall towards the center of the Earth under gravity. And this will keep happening, and eventually you will end up forming the start of the Earth's core. Okay. So the next question is well, the Earth's core is pretty big. So where did all the iron to form it come from? Well, we have a couple of models. We have what's referred to as the equilibrium core formation model and the disequilibrium core formation model, also sometimes referred to as the giant impact model. Okay, so let's think about the equilibrium model. So okay, so the situation is as we've just described. We have our silicate magma ocean. It's saturated with iron, so we get this iron liquid forming. The iron liquid is essentially coalesces to form droplets. Those droplets become heavy enough that they begin to sink towards the center of the Earth, and they begin to form the Earth's core. So everything going well so far. So as the temperature continues to drop, eventually we're going to reach the point where we're actually going to start crystallizing silicate minerals out of the magma. And the first common silicate mineral that we're going to start crystallizing out from our magma ocean is going to be one of the magnesium iron silicates, the minerals that make up the mantle. Okay, because they can stand the highest pressures and temperatures. And so we would have very likely seen minerals like olivine or ringwoodite or maybe even silicate perovskite making an appearance. They would have been the first minerals to form, and those crystals would have floated around in the magma ocean until they grew and they become so large that they too were too heavy to be supported by the magma, and they would also begin to sink towards the center of the Earth. And so over time, what would happen is you would have this iron nickel alloy core, and then around it you would build up a mush of iron magnesium silicate crystals, something like olivine or ringwoodite or silicate perovskite. So you would have this situation. Here's your core that formed right at the beginning. This is made up of these iron magnesium silicates, and however, our magma ocean is still saturated with iron. So you still have these iron droplets forming, but obviously they can't fall straight to the core. So the iron droplets are falling down and they're getting stuck at the top of this layer of mush. And so what do? Well, it just so happens we're lucky that they're very, iron nickel alloy is quite dense, and so it will squeeze through the gaps between these olivine crystals, and it will slowly make its way to the core. So this is the basic process for equilibrium formation. And by the way, we can actually see this kind of material here. This is the type of meteorite called a palisite. And you can see here are these crystals of these iron magnesium silicates. And you can see in between them, we have the iron nickel alloy. So, all right, everything so far seems to be matching the data that we have. So what about the disequilibrium model? Well, the disequilibrium model is helpful in a couple of respects. One in particular, the disequilibrium model helps to kind of explain, how the Earth ends up with such a large core, compared to its size. The Earth's core is a little bit too big for the diameter of the planet. So in the disequilibrium model, things are running exactly the same as the equilibrium model. We have our magma ocean, it becomes saturated with iron, the iron droplets fall to the center of the Earth. Essentially everything is exactly the same so far. So then what happens? Well, in the case of the disequilibrium model, it states that every once in a while the Earth would get hit by something big. And this is actually probably quite accurate, especially in the latter stages of planetary accretion. And so what the model suggests is, well, if the Earth gets hit by something big, well, when that projectile hits the Earth, it's obviously going to melt, or at least most of it will melt, and a lot of it will get incorporated into the Earth. However, the core of the projectile is going to be very big and very heavy. And so because it's so big and heavy, it's not going to sit around for very long. As soon as the two planets are combined, the core of the projectile is going to drop very, very quickly towards the Earth's core. It's going to fall fast. And it's going to fall so quickly that the core from this projectile will not have time to fully melt and become incorporated into the magma ocean. So therefore it will never have equilibrated with the magma ocean. And so that means every once in a while you'll get this large impact, you'll get this huge chunk of iron nickel alloy just drop through the magma ocean straight to the Earth's core, where it will then become incorporated into the Earth's core. And so you're thinking, well, what about this layer of mush here? Well, if you think about it, a core of a planet the size of Mars, let's say, being added to the Earth, well, that core is just going to go straight through this layer of mush as if it's not even there. So the layer of mush does nothing in terms of stopping what we see. So in terms of the disequilibrium model, when you think about it, it makes perfect sense with respect to very, very large projectiles hitting the Earth. In terms of the equilibrium model, on the other hand, well, it seems to fit and be more accurate when compared to the data that we have. So when it really comes down to it, it's difficult to pick which model is actually going to be, the more accurate, explain more accurately how our core formed. It's probably going to be a, 90% equilibrium model, and then every once in a while you'll get a, bit of mantle from another bit of core from another projectile just thrown in for good measure. So, it's not really a great explanation, but it kind of gets you to where you want to be. Now, obviously, once we start crystallizing out olivine or other iron magnesium silicate minerals, well, we're going to start crystallizing out silicate minerals in a consistent, continuous series. So if you remember this diagram, this is the Bowen's reaction series, and if you remember it, simply gives you a general idea of what minerals will crystallize from a generalized magma, given changes in temperature and magma composition. So we know that our silicate magma will initially crystallize out olivine, which will float down and settle out as a layer on top of the core. We know that after the olivine starts forming, we will eventually get pyroxene forming, a calcium iron magnesium silicate, and we will also have calcium rich plagioclase feldspar forming. So we'll have olivine, pyroxene and calcium rich plagioclase feldspar. In the case of the olivine and the pyroxene, well, they're quite heavy minerals. They'll sink to the centre of the earth and settle out on top of the mantle. In the case of the calcium plagioclase feldspar, it's going to do something a bit different. So it's unsurprising then that olivine and pyroxene are the two major minerals in mantle rocks. If we just go back for a second, just jump back all the way to, where are we, this picture here, you can see most of this is this apple green mineral, which is olivine, and every once in a while you'll see you'll have this odd dark green fleck, that's the pyroxene. Also some of these darker brown flecks could also be pyroxene as well. So these two minerals go to form the Earth's mantle. So what about the calcium-rich plagioclase feldspar? Well, calcium-rich plagioclase feldspar is actually less dense than the silicate magma. So instead of sinking towards the centre of the Earth, it'll actually float on the surface, and it will begin to create the Earth's first crust. And if you want some kind of idea of what the Earth's first crust will look like, look at the lunar highlands. So the lunar highlands are the white bit of the moon. And so what you have there is you have a rock called anorthosite. And anorthosite consists of nothing but plagioclase feldspar, more accurately, very calcium-rich plagioclase feldspar. And so it's pretty likely that the Earth's first crust would have looked something like the lunar highlands. In terms of the stuff that isn't being used to make these minerals, so think about it. We've used iron and nickel to make the core. We've used magnesium, iron, and a little bit of silicon to make the mantle. But what about all the other stuff? The sodium, the potassium, the aluminum, most of the silicon. It hasn't been used for anything yet. So far, these elements have behaved incompatibly. They haven't gone into a mineral phase. So they're just being left behind in the magma, and the amount of them in the magma is just getting more and more concentrated. So what's going to happen with those? Well, this process is called fractional crystallization. The removal of some things which are compatible with the minerals crystallizing. So as we can see here, we lost the iron and the nickel. Then we had magnesium, iron and silicon being removed to make the olivine and the pyroxene, which makes the mantle. We then had calcium and silicon being removed to make the anorthosite crust. And then as more and more olivine and pyroxene and anorthite are produced, calcium plagioclase feldspar are produced, they're stripping out calcium, magnesium, iron, a little bit of silicon, but as discussed, the sodium, the potassium, the aluminum, they're not being used. So they behave incompatibly, and they get left behind in the residual magma. And so eventually what's going to happen is you're going to end up with this body of magma trapped between the anorthosite crust and the olivine pyroxene mantle underneath. And now this magma is quite important because this magma will form this liquid will form magmas like felsic magmas, which will intrude the crust and produce things like granites. They will also push to the crust where they'll be erupted, and you'll have felsic and intermediate magmas being erupted onto the surface of the Earth. And of course, as I'm sure you know, these kind of intermediate and felsic rocks, these are the building blocks of the continental crust. And yes, the continental crust will begin forming from these very early building blocks. Now this diagram here, by the way, is actually for the moon, but the basic principle is 100% applicable to the Earth as well. Okay, so we're going to stop here, and then we're going to have a relatively short video to bring this presentation to a close. So once again, get up, have a walk around, get a glass of water, and then come back when you feel ready.